A book entitled Learning the Brainstem, or LTB for short, is in print. Why not have short videos to capture the book's main points? The voice you hear is AI generated. We use AI to facilitate translation into multiple languages. This video, LTB5, passes from the level of the third cranial nerve or CN nucleus in the direction of the fourth CN nucleus. We are well into the LTB series. I will not repeat too much of LTB videos 1 through 4, but all the brainstem images that I use are a bit unusual in one respect that bears re-emphasis. We orient our brainstem photomicrographs as we might visualize them radiographically. So, hemibrainstem to the right is left midbrain and the hemibrainstem to the left is right midbrain. The axial MR image identifies the approximate axial level of the photomicrograph. For the sake of brevity, I'll not rename structures that we have identified in previous LTB videos, but I do mark 3 with orange dots here. But we see a great deal more at this level than we have visualized in previous LTB videos. Let's start by re-identifying a midline landmark. The red dot sits in what structure? I'll give you a moment. The cerebral aqueduct, or aqueduct of Sylvius, is surrounded entirely by grey matter. And there is no posterior commissure, because now we are at an axial section below it. Let's work our way through the vertical midline, beginning ventrally. You can orient yourself in an enlarged image with respect to the cerebral aqueduct. The blue dots now sit in the interpeduncular fossa in both images. The yellow arrow points to a ventral tegmental area, which we will abbreviate as VTA. The VTA is significant for 2 reasons. First, in the 1920s, a man named Tsai from the University of Chicago noticed dark neurons there. It was later learned that dopamine neurons occupy VTA as they do in the S-ANPAS compactor. The second reason why the VTA is important has to do with why it is rather uniformly grey. Yes, there are very dark fascicles parallel to the midline that pass through it. Those are fascicular fibres of cranial nerve, or CN3. But the grey background speaks to the fact that a median forebrain bundle extends from VTA and will head to corpus striatum and much of the forebrain. The median forebrain bundle is the pathway by which dopamine projections get to their destinations. We will have quite a bit to say about the nucleus shaded in green. For now, let's just say this. The plural that we use in the title to this video, levels of CN3 nucleus, is intentional. The large CN3 nuclear complex occupies midline vertical space from even above the level depicted in the slide, all the way down to the CN4 nucleus. Around the cerebral aqueduct, quite circumferentially, is grey matter. Previously, we saw central grey higher up in the brainstem, and we identified eye movement-related nuclei at those higher levels. The grey matter at this level, called the periaqueductal grey, or PAG, is unique in 2 respects. Sensory fibres mediating pain end in the PAG and do not pass to thalamus. Second, the PAG receives information from many locales. I'll mention just one, since it is relevant to our discussion in our next video, LTB6. It receives afferents from reticular formation. PAG also projects to reticular formation. Finally, dorsal to the cerebral aqueduct and the PAG are structures marked by blue dots. The superior colliculi are best visualized if we think about the dorsal aspect of a whole brainstem, as we see in the gross anatomical image to the right of the screen. There, as in the axial section, the superior colliculi are marked by blue dots. The so-called quadrigeminal plate consists of superior and inferior colliculi. The inferior colliculi are marked by white, not blue, dots. Think for a moment about the distance between blue and white dots in the gross anatomical image. There can't be much more than 5 mm between them in the vertical plane. But within that distance, the microanatomy of the CN3 complex changes. For a neurologist, knowing something about the microanatomy matters. In this slide, I identify 6 functions with which the CN3 complex must deal. Actually, the list is incomplete because I don't mention accommodation, for example. Nevertheless, each aspect involves a separate CN3 subnucleus. And in fact, medial rectus has two subnuclei that are separated in space. At the level of our axial section, more or less all subnuclei are present. I say more or less because the so-called central caudal nucleus, which has to do with levator palpebrae, is centered very low, closer to CN4 nucleus, which is a bit below our current level. You notice, perhaps, that I colour superior rectus in a different colour. Superior rectus is the only extraocular muscle innervated by a contralateral CN3 subnucleus. There was a rationale to how I ordered the functions of CN3 nuclear complex in the last slide. Our photomicrograph is enlarged and fuzzy, but we can say several things, with the help of some colour and some grid lines, as in a tic-tac-toe. First, the more ventral in the upper part of the green triangle, the more likely you are in the territory of the subnuclei for superior rectus and inferior oblique. These two muscles are involved in moving both eyes upward. Here's the reason why I obsessed over talking about the levels in plural of the CN3 nuclear complex. Depending on how high or low in the midbrain you happen to be, the subnuclei you will find, in all likelihood, will differ. Above our current level, the majority of the CN nuclear 3 complex is comprised of subnuclei for medial rectus and inferior rectus. In fairness, however, medial rectus subnuclei, there are two of them, are both large, and they are present at all levels throughout midbrain. Sticking to our current level, in the middle tier, the more likely you will encounter inferior rectus subnucleus, which is involved in moving the eyes downward. Third, in the lower tier, the more likely you will encounter a nucleus that projects to ciliary ganglion related to pupillary constriction. The so-called Edinger-Westphal nucleus is really a two-part thing. The part that we think of most commonly, and the one that we point to in the classroom, at the dorsal aspect of the CN3 nuclear complex, is not quite so clear in reality. The preganglionic neurons of the Edinger-Westphal nucleus are rather dispersed throughout the dorsal CN3 nuclear complex. But in this so-called lower tier, again, location in vertical space is important. If you are lower in the midbrain, the most likely dorsal CN subnucleus that you will encounter is the central caudal nucleus, which innervates bilaterally the levator muscles that lift the eyelids. Under normal conditions, there is tonic inhibition of the central caudal nucleus by fibers originating at the level of the posterior commissure. Here's a last look at the CN nuclear complex, now between the parallel vertical lines. Very much in the midline, as Richard Perlier described in 1889, there is a midline subnucleus named after him, a nucleus Perlier. It is present even above our current axial level. Nucleus Perlier was once thought to be involved in convergence, but nowadays people think that it's involved in upgaze. Nucleus Perlier and the central caudal nucleus mentioned previously are unpaired, unlike all other CN3 subnuclei. We said that we would get to as low as CN nucleus 4, but I haven't shown it. The right red arrow points to right CN4 nucleus. The left red arrow points to the midline CN3 nucleus at nucleus Perlier. But subnuclei of CN3 are on either side. A lot happens lateral to the midline, especially with respect to white matter between these two levels. We address what happens in LTB 6. Congratulations! In the last few minutes, you negotiated some detailed brainstem anatomy. As always, thanks for watching.